Hi friends, welcome to follow up. Let's have a look at problem 222, count complete tree nodes. In this video, we're going to share a solution based on recursion. And in the follow-up video, we would like to explain a solution based on binary search. So first, let's look at the problem statement. So here we are given the root of a complete binary tree. So we want to return the number of nodes in the tree. And the main requirement for this problem is the following. So we need the algorithm run in less than O(n) time complexity. So that's the main requirement. So for this problem, so we have three examples. Example 2 and example 3 are two edge cases, right? So we return 0 for empty tree, and we return 1 for single node tree. And example 1 is the generic case. So in this case, so we have 6 nodes in total. This is the return. And here, the number of nodes in the tree is given in this range. So actually, the node value is not essential for this problem. And the third one is that the tree is guaranteed to be complete, right? So for this problem, because this is a binary tree, so if we want to count the nodes, so actually we can think of traversal, right? So any traversal plus counting will do for this problem. But we just need to pay attention to the time complexity. Let's just demonstrate that that comment. So for example, I can quickly write a solution based on traversal. So if not a root, so we're going to return 0. Otherwise, we're going to return 1 plus, let's count the number of nodes in left subtree, right? And then count the number of nodes in right subtree. So then this will give us the total number of nodes in the binary tree. So let's do a test directly. Yeah, it will pass. And however, so this solution, because we do a vanilla traversal, so the time complexity will be O of n. So here n is the number of nodes. So with that said, let's look at a slightly better solution. So here we want to improve the time complexity. So actually we can pay attention to the depths of the left subtree and the right subtree. So first, if they are equal, then the left subtree must be a full tree. For example, you can see example 1. Let's look at the root 1. Then its left subtree has 2 levels, and the right subtree also has 2 levels. And due to the definition of complete binary tree, so this indicates the left subtree must be a full tree. So this is the one case. So if the 2 levels are not equal, right, it actually basically says that the left subtree has a larger depth than the right subtree in this complete tree setting. So in this case, basically it tells us the right subtree must be a full tree. For example, if you look at this tree, so this one, the left subtree has depth or has 3 levels, while the right subtree has 2 levels. You can see that the left subtree is not a full tree, but it's a complete binary tree itself. And then the right subtree is a full tree, right? So that's actually our main observation. So we are going to write a very simple recursion solution based on this comparison. So here, actually, we also need to know one point. For a full tree, it's very easy to compute the number of nodes according to the depth. For example, here, the total number of total depth is 3, right? So here, I'm going to count in all the levels. So here, depth, I define it as the number of levels. So here is 3 levels, right? So in the first level, we have 1 node, that is 2 to the power 0. In the second level, we have 2 to the power 1. And in the third level, we are going to have 2 to the power 2, right? So if you mark the levels as level 0, level 1, and level 2, so this 2 raised to the power of level indexing is the number of nodes in that level. So this is nothing but 2 to the power 3 minus 1. So this is very simple to compute, and it's elementary math. So this 3 is nothing but the total number of levels, or I can call it depth, is 3. So now with this 2 pieces of information, one is the comparison of depths, and one is the computation for a full tree. Let's write a solution. So here I'm going to copy this part. Let's call this one version v1. So this will be our solution here. So first, I guess we can get the depth for the tree. That's very simple. So let's write it as a method, maybe. Let's see. Define get depth self root. So if not root, so we are going to return 0. Otherwise, we are going to return 1 plus self get depth root left, right? So we just need to look left subtree, and then once we arrive at the bottom, we are getting the number of levels. So here let's call it depth. And then what we want to do, let's see here. First, let's treat an edge case. If not root, so we're going to return 0. This is for sure. And then we can get left depth and the right depth. So the self get depth root left, and the self get depth root right. And then we do comparison, right? If left equals right, then it says that the left subtree is a full tree. So the left subtree will have something like this, return. So what we want to return? The number of nodes in the left subtree, because it has such number of levels. So what we are going to want to do is to do this. So 2 to the power L, right? Then plus, so because this is a level, so here the level is like this. So this 2 to the power L minus 1 is the number of nodes in the left subtree. And then we need to add the root itself. So let's add 1. And then we add self count nodes for the root right, right? So that's one thing. Another case is that the left and the right are not equal. So in this case, we are corresponding to here. It means that the right subtree is a full tree. Then what we want to do is we return, so 2 to the power r minus 1. So this is the number of, let's use some parentheses here. So this is the number of nodes in the right subtree. And then we plus the node, the root itself, and then we do self count nodes root left, right? So certainly you can combine these two to get 2 to the power L. And you can combine these two, you get 2 to the power R, right? But I guess writing this one plus 1 and plus right, and it makes the logic more clear. So with that said, let's first do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So I guess that's basically about it for this problem. So let me make some comments. So first, in this problem, so leetcode mark it as an easy one. So indeed, if we do not consider term complexity, it's very straightforward. You can use any traversal plus counting, right, as in solution we want. But if we want to use better than linear term complexity solution, we need to think a little bit. So here we wrote a recursive solution, right? So here let me analyze the term complexity, right? So here I will use this as a comment 2, right? Analysis of term complexity, right? So if let's assume we have d levels. So in this example, we have 3 levels, right? So if for the full tree, the d levels, so we have this number of nodes, 2 to the power 0 plus 2 to the power 1 plus up to, say, 2 to the power d. So this is nothing but 2 to the power. So here we have 0, 1 up to d plus 1 terms. So d plus 1 minus 1, right? So if the last level just contains one node, a single node, so the number of nodes will be 2 to the power and d plus 1 and d. So we do not consider the last level, so we will have d minus 1 levels. Then this is the total number of node, right? And then we plus 1. So in general, so for the tree with d levels, the number of node will be in this range, 2 to the power d. So less than equal to 2 to the power d plus 1 minus 1, right? So I guess here let me see. So here is 2 to the power. Let me do some computation, right? So d levels. So here is d minus 1. So here will be d, right? So here, let's see. We would have. So this one will be 2 to the power d minus 1. And here we will have 2 to the power d minus 1. Minus 1. So that's if we have d minus 1 levels in total. And then we are going to add 1. So this we will have 2 to the power d minus 1, right? So overall, so the d and n will have such a relation. D is roughly log 2 of the n, the number of nodes. So in our solution here, so we compute the depths. So each time we compute the depths, which will take d, time complexity with d, compute depths. So time complexity will be O of d, right? So here, when we do this traversal, so each time we need to compute the depths. So here we use actually another OD operations, right? So overall, the time complexity will be OD square. So OD square is nothing but O of logarithm 2 n square, right? So now let's ignore the base for this logarithm. So it's basically O log n to the power 2. So let's see. Let's not this is like this, right? It's log. Let me specify this. It's log n times log n. So up to a constant. Let's write like this. So notice this is not log n square, because this is nothing but 2 times log n. So here we can write up to a constant if you like. So overall, it's a square of logarithm n. So it's much smaller than linear time complexity. So with that said, I guess that's about it for the current video. Thank you.